Okay, ladies and gents, this is going to be mechanism 3. So for mechanism 3, you might see something like C2H4 becomes C2H4Cl2. So if you're to draw that out, just so you can be very sure about what's going on. This is what it would look like. So again, this is very obviously an addition. You've added on, in this case, Cl2 is your reagent. So if you have to describe the mechanism for ionic addition, it will be with Cl2 as your reagent. So looking at Cl2, in terms of looking at what its intermolecular forces might be within it, or is it a polar bond, polar molecule? So Cl, if you were to find the electronegativity values and take away one from the other, the answer would be equal to 0. So we know if it is less than or equal to 0.4, then this is a non-polar bond. So naturally itself, it is not, there is no delta positive and delta negative, it is not polarized. But as soon as this molecule gets near the ethene double bond, the double bond polarizes it. So we've said what this means is it makes this part of the molecule delta positive, it makes this part of the molecule delta negative, and when we draw, we always keep the perpendicularness of the approach of the small molecule to the double bond. We then have to include the idea that the electrons in the double bond go after this delta positive chlorine, and the electrons in the shared pair go towards this chlorine. In our second diagram then, we show the carbocation that's formed. So in this case, the carbocation can also have a different name. So when we added bromine to a carbocation, it was called a bromonium ion. So this is the intermediate, and we have said that the intermediate is key to proving that it's an ionic addition mechanism, and we'll talk about that in a little while. So as well as being called a carbocation, so again we're recommending every time you draw a carbocation structure you write in the words. This can also be called a chloronium ion. And the reason I give you this is in case it's written in a question, then you will know it. So we have our chloride ion down here, our fully negative, no partial charge, fully negative charge, and this negative anion is going to go after our carbocation, forming us. We've said we're always putting our halogens on the sides. The chlorine will have 3 outer shells here, so 1, 2, and 3, as will this. So they will try to orientate themselves as far away from each other as they can. So for that reason, we are going to put them to the sides just to be safe. There's no issue. Then for the SEC, it's very straightforward for them. So it doesn't matter which chlorine is carbon 1 or which carbon is chlorine 2 because they've got something on each one. But in terms of our naming, we have to give the numbers, and the fact there's 2 chlorine turns it into dichloro, and because it has 2 carbons and it's saturated, dichloroethane. So we always put in our product when we're done, just so then the SEC know what it is you have made. So the 3 diagrams will always get you the vast majority of the marks. We reiterate the fact that we have, in this case, the polarization of your chlorine. So that is the Cl2 becoming Cl, a delta positive and a delta negative. And we also have heterolytic fission of the chlorine, so it's implied in the diagrams as we go from diagram 1 to 2, but we write it like this. to just guarantee that if the SEC are looking for it, then you have hit their mark scheme. So just to remind you, heterolytic fission means that if these are the electrons in the shared pair, hetero means if you're heterosexual, the opposite sex. So here the split is uneven. So the electrons that come to this side make the anion, and the fact that this now has missing one electron turns it into a cation. In terms of then our other two pieces of evidence, if we're going to be very economical and succinct about what it is we've made, we can say that the chloride ion attaches to the carbocation, forming 1,2 dibromo, oh, apologies, dichloroethane. So as you've said, it's this question down here, in the red box down in the bottom left, that statement is the most important one in terms of a piece of blurb. If you know your diagrams, you're going to hit your marking. So again, we're then going to be looking for pieces of evidence. And it all comes down to the carbocation and the fact that you now have this positively charged moiety in your solution, and any negative ion that is present will attach to your carbocation. This does not want to play ball. Okay, when in doubt, erase, erase, erase. So thank you for your patience. So in terms of the pieces of evidence to prove that it is ionic addition, our carbocation looks like this. And we have said any negative ion is going to be attracted to it. So they may mention the fact that in this instance, it would probably be, you would give a piece of evidence. So if you had bromine water, then in that case, in your bromine water, there would be a very good chance, because the double bond in the ethene would polarize bromine, that you might have bromide ions in there. And you would also have your water dissociating to give us the OH minus ions. So if that was the case, then the carbocation would form two different things that would be unexpected. So the first one would be the Br minus would go for the carbocation, and if that was the case, then we would get this molecule, and again we name alphabetically and number alphabetically. So this would be 1 bromo, 2 chloro, and it's got 2 carbon saturated molecule ethane, and this is unexpected. So the other option for our carbocation is if we have the OH minus from the dissociation of water. So that is going to go for here, leaving us with so the OH group turns it into an ethanol. We will name from this side. So we now have 1 chloroethanol. And again, this is an unexpected product. So Therefore, it proves the mechanism is ionic addition because of the presence of our carbocation. So that ends our third mechanism.